So very good morning. So let us see the next lecture. In the last lecture, we have seen the Swedish slip circle method to find out the stability of finite slope. In this method, we have discussed two types of soil. First is the analysis of purely cohesive soil, that is phi u is equal to 0 analysis, and second, the analysis of soil both cohesion and friction, means C phi soil. It can be applicable for all the types of soil. Phi is equal to 0 soil, we have established this particular relations to find out the factor of safety of the cohesive soil by assuming the, you can see this is the figure that what we have actually explained last time. And finally, we are deriving the factor of safety value for this, which is Cu L arc R upon W X bar, that you can actually derive from solving this particular trial slip circle. You can take as many as trial slip circle if you want. The trial slip circle corresponding to minimum factor of safety, you can say it is a critical slip circle. Here still I am not defining where is the center for taking this particular trial slip circle, and the radius, you can take as many as radius as a trial. Now let's go further. Then we have discussed for the C phi soils, and same way we have derived like this. Like for example, I'm just discussing this method again because I would like to complete this in a more detail today. So I'm discussing this method again and I will go forward. So in order to test the stability of C phi soil, trial slip circle is to be drawn, as in the case of previous method. The material above the assumed slip surface is divided into the number of vertical strip slices. For example, if you see, this is, I'll just sorry. If you see, first what you need to draw is, let's say you draw this first, this slope with some scale, right? So if you take, you can say the 1 centimeter is equal to something, and you try to draw this particular slope like this. Then choose some center. This is also random. Choose some center. So suppose I am assuming this as a center at present. We will discuss how to locate this particular center, which is later on. But for time being, just imagine this is a center that you have chosen, and take various value of R and draw the circles on this slope. You can draw number of such trial slip circles. I'm doing the analysis of one trial slip circle and show it to you. Same way you can actually do the analysis for number of trial slip circle and find out the factor of safety, right? So first you are going to draw this particular trial slip circle with one value of radius R, and you have drawn this particular circle like this. So this is a circle that you have drawn. I'm just putting, you can say just overlapping these things, or should I change the color so that you will actually probably you will understand more in a more better way. So this is what the circle you have drawn. Then what you need to do is, you need to divide this particular circle into the number of trial slip. For example, this particular circle I have divided into the number of trial slip with equal spacing. You can take number of trial slip, spacing, that is also you need to decide by you. As you are taking more number of strips, your accuracy of analysis will be more, right? So for example, I have taken, you can see 1, 2, 3, 4, 5, 6, 7, 8 trial slip, trial slices of this particular circle. Also you find out the midpoint of each. So for example, this dotted line you can see, so this is the midpoint of each slices. That is what I have drawn here. Can you see? So this is the midpoint I have drawn. So this is the midpoint you draw for each 8 trial sleeves. Now let's go further. The forces between the slices are neglected and each slice is assumed to act independently as a column of soil of unit thickness and width B. That is also we have seen last time. The weight W of each slice assumed to act as a center, at its center. Okay. If the weight of this slice is resolved into normal and tangential component, the normal component will pass through the center of rotation and do not cause any driving moment in the slice. Let's see how the things will be. For example, now what you need to do in the next step is, once you analyze this in this way, now you can, now from each midpoint, first of all, you need to put the weight component. So first you measure this length. Okay, first you measure this length, like this is the length, you can see this length you measure, and the same you put it with this particular line. So I'm drawing the line which have a length exactly equal to the this. Okay, and same way this length, this I'm just putting here, and same way this length I'm putting here, and so on. W component I'm putting for each of this triangle. Okay, so this is the W which is going in a downward direction, W which is going in a downward direction for each of these sleeves. Each of these slices I have drawn the W component which is equivalent to this vertical line. Now this you need to resolve into the two component. One is the normal component and other is the tangential component. So the normal component will pass through the center of rotation. Now it is audible. Hello. Hello. Now it is audible. Hello. Yes. Okay. So again, I'm repeating. Just see for another slice again. I will just repeat this procedure again. Just see for this, let's say for this fourth slide. Okay. Now just you take the slice. First you plot this weight component. So whatever the length of this, you plot it here as a W4. So you can say this length and this length. This exactly you are plotting here. Okay, same length. So this is your W component which goes in a downward direction. Okay, now this point and this point, center of rotation, you need to join together with help of the scale, and you pass the line through this point, which will give you the normal component. Right now I do not know what is the length of it, but from here you can draw a line which is perpendicular to this. So this will be perpendicular, which intersect this W point. So this exactly you will get this length plus this length. So this length from here to here, so you can say this is the leftward side, you are going from normal component, so arrow is this side, and this is normal component. So you will get this normal as well as tangential component of this particular slice. In such a way you can actually draw it for each slice. If you just come over here, then you will realize this arrow is going in a rightward direction. Why? Because this W, you can plot it here, and now if you join it from here to here, sorry, I will draw this line like this. You can see this line, if you draw, then this will be passes through this, and you need to go from left to right here. So that is why this is a rightward direction. All other cases it is going in a left direction, but it is a reverse conditions. So this way you can analyze this particular slice to find out its component, which is tangential component as well as the normal component. Now let's go further. So if the weight of this slice is resolved into the normal and tangential component, the normal component will pass through the center of rotation, as we have seen, and it do not cause any driving moment in the slice, as this is going to confine this particular thing. This normal component will actually give the confinement to this particular slope, so it will not contribute in sliding of this particular slope. Okay. However, the tangential component will cause the driving moment md, which is nothing but t into r, where the r is the radius of slip circle, the tangential component of few slides at the base, which cause the resisting moment. And in that case, the t is to be considered as negative. As I said, this is in this direction, right to left. Sorry, should I go for the pointer? So you can see this is going from left to right, and this is going from right to left. So this will be actually against the sliding it is working. So it walks towards the stability of the slope, while this walks towards the instability of the slope, right? So the tangential component is varying. Now if the cohesion and the delta L, so each length of this slide, I'm supposed to say it is a delta L. If you sum it up all this delta L, it will give you the L arc, right? So as per the Coulomb's equation, you can go towards this C into delta L, which is the length of the particular, you can see the strip, which is this, into normal component into tan phi. C plus sigma tan phi. This is the, you can see the normalized form of this particular thing. Okay. Now, if you plotted this, then the driving moment, what we have calculated is sigma t. Sigma t is the algebraic sum of tangential component, which is t1, t2, t3, t4, t5. So all the leftward and the rightward, you need to do the algebraic sum. So this minus this, whatever the value comes. So this will give you the sigma t value, right? So, and this sigma t multiplied by this distance, which is r, which will give you the driving moment towards this side, slope side. Okay. So this is md is equal to r into sigma t. Similarly, resisting moment, which is nothing but r into whatever the component of shear strength that we have taken, c into sigma delta L plus sigma n tan phi, where sigma t and sigma n is the algebraic sum of all tangential and normal component respectively. If I take the summation of all this length of strips, then this will be give you the total length of the r, right? So which we have already seen earlier also, 2 pi r delta into by 360. So if you put this particular value in the factor of safety, this is nothing but resisting moment upon driving moment, then this particular equation that will become, that is CLR plus sigma n tan phi upon sigma t. From this particular equation, you can find out the value of stability for any type of soil using this Swedish slip circle method, right? Now the question is how to calculate the value of sigma n and the sigma t, right? So for that, number of methods has been suggested. For example, if you see here, in this case, what these people have done, this is been calculated with help of the graphical method. For example, just you plot this particular line just below this, okay, and just project this particular dotted line on this line. For example, I will take again, you can see the pointer again, so you will realize how to do this. For example, what I'm doing is I'm drawing the line like this exactly, which is in the this way. I'm just taking the projection. So this is the length of the line. Now for each this dotted line, I will plot this value. Can you see? And so on for each one. Okay. For each one, suppose 8 strip is there. I have plotted this particular point of a dotted line. Now measure the value of this n component. So n component, you can measure it easily. Okay. This is n2. This is from slide number 2. So whatever the value length of this, you are going to plot from here. So this length you are plotting. So probably this value will come here. Similarly, this n3, n2. So this n2 may be here, and so on. For each of the slides, you measure this value and plot it here. And then if you join it with the smooth curve, you will get, this type of curve, which has been drawn here. You can see this. Now, if you use the planimeter, or if you can actually find out, you can take any method to find out the area of this, and you will get the value of sigma n. Similarly, you might have done with the instrument also, with the help of the planimeter in the surveying. You can say find out this area, you will get this value. So that is a one method. Similarly, in the case of sigma t, same way, you are going to draw in this way. So for example, this is a line that is I have plotted. Then again, you can say plot the center point in the same way what we have done in the previous figure. So this is the center I have plotted. Now find out the value of sigma t, which is going in the leftward side. So plot against each of this line. So this is the point. This is the point. So for each point it will come. Now you can see here, these are all leftward from up to here, and this is rightward side. So rightward will go down, right? So rightward will go down. So this will come here. So then if you plot it, you can say this curve, then this will give you this way. So this plus minus this. So it will give you the algebraic sum of sigma t. Again, you can do this with help of the planimeter, or any other method you can actually use mathematically or analytical to find out this. I think the planimeter is the best way to find out the area of the irregular shapes. So this is a one method. Now, if you go towards the second method to find out this, then probably you can use this particular equation. That is the weight component. Like I will, this is what is method. Like n component, you can actually draw in this way. So for each circle, like n1, so whatever the length of n1 is here, you are going to plot it here. Then n2, whatever the length of n2 is there, you are going to plot it here. So this way, for all the lengths, you are going to plot it. Only the problem which comes here is at the last slide, because the width of the last slide is not exactly the b. So for that, this particular relation has been given n8 upon 1 plus m divided by the 2, right? So whatever the length, first and last length, that is, you need to find it out. So if I take the last length will be mb, and all the width of this slice is b, then you can actually easily find out what is the value of m. So based upon that, you can actually find out what will be the length of this, and this width of this triangle, which is equivalent to the value of b. So this way, if you take the area of this, you will get the value of sigma n. Similarly, if you do it for this t value, then also you will get the value of sigma t. So this is the second method by which actually you can do graphically. But this area is the regular shape, so it is easy to find out the value of area than the previous method. In my view, this is the most easiest method. This is the third method, or whatever the value that you have found out from this particular rectangle, that you can put it here. So like this is the area of rectangle, which is here, you are going to put it. Since you have taken, you can see the scale. 1 centimeter is equal to something, so that scale is to be converted. So suppose you have taken 1 centimeter is equal to 4 meter, so the x value is 4, right? So this is what you are going to consider. And square is written since it is the two-dimensional figure, meter, and then the density of the soil, so you will get the exact value of force in sigma n. Similarly, sigma t, it is nothing but at, this is nothing but t, this is at, that is the area of that what you have calculated from here multiplied by the scale square, right? Since it is a rectangle multiplied by the density, you will get the value of sigma t. So probably this way you can calculate the value of sigma n and sigma t. This is the final method what I'm supposed to explain here. This is probably a most easiest method, that is what I understand. Like for example, W you know. So what you do is, from this particular side you can actually find out the value of W. That is, you can very easy, this length you measure it, multiplied by the density, you will get the value of W, force, right? Now you can find out this is the particular angle theta. Let's assume this is the angle theta, right? Then you can easily resolve these two components. This is sine, right? This is sine and this is cos. So you can see this is cos. So if you see here, so W, you just put the value of W, whatever the value is here in the slice. And then if you want to find out n value, which is nothing but W cos theta. I have taken theta, they have taken alpha. So they have taken and W cos alpha. So N1, N2, N3, N4, you can calculate. Similarly, you can calculate the value of T, which is nothing but it is the sine value. But you need to remember, if the direction will change like this, as you see, all this going in a leftward side. Sorry. See, all this going in a leftward side, you can take plus. So then when this slide will go in a positive direction, you need to take the minus in this while you are finding out this sine component of this. Okay. And this length you can actually easily find it out, or you can easily measure it out, right? So this way you can actually calculate the value of sigma n and sigma t. And if you put this value of sigma n and sigma t into the equation, what we have derived here, then you can easily calculate the value of factor of safety for the particular slip circle, right? So this is the method which is being called as Swedish slip circle method. I hope it is very clear. Very fundamental method, widely used in the field to find out the stability of the slope, right? Now let us go further. So here in this method, what we have done is, like for example, suppose this is my slope is there. We have defined here, I have said you can take the center anywhere here. Am I right? We have not defined because there is a big space here in which you can actually take the center. I don't know. You need to take the center here, 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 here. I do not know exactly. So for that, one method has been suggested, which actually find out what is actually the probable location of the triangle slip circle. And this method is known as method of locating the center of critical slip circles, right? So this method has been given by Fellenious, and that is why this method is known as Fellenious method of locating the center of slip circle. How to locate this? Let us see this. In order to reduce the number of trials to find out the center of slip circle, Fellenious has given the method of locating the locus on which the probable slip circle may lie. For homogeneous C5 soil, the center of slip circle lie on line PQ. If you see, this is the line PQ. I will again go to my pointer option. So this is line PQ. So probably this will go on this line PQ. How to locate this line PQ? That is the question that we'll see later on. So how to do this? So what you need to do is, first, let us try to understand how these things will, how to locate this particular trial slip circle. For example, first you need to draw this particular slope with some scale, as we have done in the last way. So this is my height of the slope. So whatever the height is there, you just plot it like this. Am I right? And this angle, slope angle is given. So this I is given. So you plot it, and you can say the first you draw this particular slope with some angle. Now, in this method, uh, there are certain guideline has been given. So there is a directional angle has been given. For example, suppose you have a slope angle. There are various slope angles has been given, like 60 degree, 45 degree, 33 degree, 26 degree, 18 degree, and so on. And for that, the directional angle has been given, alpha and value of beta. For example, if I see alpha and beta for the slope of 1.5:1, that is 26 degree and 35 degree. So if I use this, then I will draw for that particular slope. I'm taking the value of alpha considering the corresponding value of the slope. If my slope is 1:1.5, then I will take the value of alpha correspondingly, and I will draw this particular line in this way. And then the beta, this beta, please remember that this beta is corresponding to horizontal, while the alpha is corresponding to this slope line, right? So I will actually find out the value of beta here, and I will draw this particular line which cuts at some place, right? Like this. Okay. Now, so once you locate this two line, then what you need to do is from this particular point, first you need to go downwards with the value of h here. So this is the value of h. I'm going to plot a downward direction. I will get this particular point. And from this point, I need to go 4.5 times the h on this side, so that you will get the value of q here. Now you need to draw a line which is passing through this particular point P, and join this particular value. Then you can say that your location of the center which is on this line. So now what I've done is I'll locate the line of the center. Means my center may be here, maybe here, maybe here, maybe here, I do not know. But what I've done is I've reduced from this particular space to just only the line. So on this particular line, my trial slip circle will be there. Now for that, what I will do again next. So for each of this circle, I will take, the regular interval of the centers, and I will draw the trial slip circle with assuming some value of r. So from each of the center, I will draw the slip circle here. I will analyze with the method of slices and find out the factor of safety. Whatever the factor of safety is coming, that is I will plot against this. Same way for second circle center, third center, fourth center, I will locate this factor of safety and I will draw the smooth curve. The factor of safety corresponding to the minimum value, which will be your permanent critical center for this particular slope. So for that, you need to take the number of trials. So you have reduced the number of trials to the significant number, right? So this way, you can actually do the stability analysis, and also you can locate the center of trial slip circle. So I'm stopping here, and I've covered this particular method in detail. So if you have any questions, you may please post. I'm able to actually answer it.